Today, we're talking about something called g-B3N3C, which is, well, it's a material that, by all rights, probably shouldn't even exist.
Welcome to Mandora. Now, this isn't going to be a super deep dive. Think of it more as a journey into a really big idea, just simplified.
So, let's just start with a crazy question. What if you, yes you, could build a material from scratch, literally atom by atom, to give it any electronic property you wanted? What would you make? You know, maybe a perfect semiconductor for the next generation of computers? Or what about something that just sounds completely impossible, like a magnet made from parts that aren't magnetic at all? It sounds like pure sci-fi, I know, but hang with me here, because by the end of this explainer, you are going to meet a theoretical material that promises to do exactly that, and maybe even a little more.
All right, so to really get this new material, we've got to meet the superstars of the 2D world first. Let's call them the Dream Team. Okay, on one side of the ring, you've got graphene. It's just a single layer of carbon atoms, and it is famous for being the best electrical conductor on the planet. And on the other side, we've got hexagonal boron nitride. It looks almost the same, but it's a perfect electrical insulator. So one lets electricity flow like a river, the other stops it dead in its tracks. They are total opposites.
So the idea seems pretty simple, right? Just combine them. You could build custom circuits, like a microscopic patchwork quilt. Well, that's where we hit our first and biggest challenge. Here's the problem. Scientifically, they're called naturally immiscible, but a much easier way to think about it is they're like oil and water. They just refuse to mix. And when you try to force them together anyway, you get this. It's a mess. You get wrinkles, you get defects all over the atomic structure. The result is just chaotic, totally unpredictable electronics, which makes it completely useless for building the tiny, precise devices that we actually need. It's a huge roadblock.
But what if there was a way to make a perfect, orderly mixture? Okay, let's bring in the hero of our story, this theoretical material called g-B3N3.
And just look at that. This right here shows you how elegant the solution is. There's no messy patchwork, no chaos. Instead, you've got this perfectly repeating, beautiful lattice. The yellow balls are boron, the green ones are nitrogen, and that one single gray atom, placed with total precision, well, that's the carbon atom that changes everything. So what is g-B3N3C really? It's a brand new 2D material that was predicted using some seriously complex computer simulations. And the key idea is its structure. You take a perfect sheet of boron nitride, you pluck out just one atom to create a little hole, a vacancy, and then you slot a single carbon atom right into that spot. The whole process, in theory at least, is just beautiful in its simplicity. Step 1, start with your insulator, the boron nitride. Step 2, pop out one atom. Step 3, substitute it with one atom of your conductor, carbon. That's it. It's like building with atomic-level Legos.
Okay, now this is where things get really, really cool. It turns out that this one super simple recipe can actually create two very different versions of the material, and each one has its own kind of incredible superpower. So how does that even work? Well, it all comes down to where that one little carbon atom decides to connect. So on the left, we've got the alpha form. Here, the carbon bonds to the nitrogen atoms. This makes a super stable semiconductor. But on the right, you have the beta form. This is where the carbon bonds to the boron atoms instead. It's a little less stable, but it creates something totally mind-blowing, a magnetic metal. I mean, think about that. Two completely different materials from the exact same ingredients. Let's look closer at that alpha form. It's got something called a band gap of 1.22 electron volts. You can just think of a band gap as the cost of entry for an electron to start conducting electricity. So why does this number matter? Because 1.22 eV is pretty much the perfect sweet spot for building things like computer chips and light sensors. It's a tailor-made semiconductor. And now for the beta form. This number here, that's its magnetic moment. And what's absolutely nuts about this is that the material has zero traditional magnetic elements. No iron, no nickel, no cobalt. It's just boron, nitrogen, and carbon. And yet somehow it's magnetic. The magnetism literally just comes from the way the atoms are arranged. So, okay, we have a custom-built semiconductor and a magnet made out of non-magnetic stuff. What in the world does this mean for the future? Why does this all matter? Well, the potential applications are huge. The alpha form could let us create tunable electronics, where we design a device's properties down to the last detail. But the beta form, oh man, that opens the door to a whole field called spintronics. See, right now our electronics use an electron's charge as a simple on or off switch. Spintronics would use its spin, a quantum property that's like a tiny magnet pointing up or down, to add a whole new layer of information. We're talking about data storage and processors that could be way, way faster and more efficient than anything we can even imagine today. And hey, don't just take my word for it. The actual researchers who predicted this stuff call the beta form, quote, the first theoretically predicted metal-free magnetic material. This is brand new territory for science. This is a picture of the electron spin density. Those purple clouds are basically showing you where the magnetism is coming from. This is literally what magnetism without magnets looks like. It's a property that's born from nothing more than geometry and quantum mechanics. It's wild.
So, we're left with this really tantalizing question. Now, g-B3N3C is still just a theory, right? We haven't built it yet, but it represents a massive shift in how we think about making stuff. Could this whole approach, designing materials one single atom at a time, be the key that finally unlocks the next generation of quantum computing and electronics? The possibility is, well, it's pretty electrifying.